podcast is brought to you by LMU Munich.
Thank you. Thank you very much. So this is the last lecture for today. So we could call this lecture something like, I don't know, black holes as brains or something like that. And the reason will be clear in a moment. So the idea would be to look at the questions that we have in black hole physics from a different angle, pretty non-standard. I mean, that's obvious that it's always, whenever we have a phenomenon that we don't understand, it's always useful to look from different angles. So this will be sort of an angle from the perspective of a particle physicist. I'm a particle physicist and a model builder, particle physics model builder. That's what we do to understand different systems, like starting from standard model, grand unification, and so on. So what we try to do is to build models that so what's the idea of a model? The idea is that you have a complicated phenomena, and it could be technically extremely hard to compute something right away through brute force. But there are things that are essential, and there are things that are completely secondary. And what you want to do when you build models, you want to reduce the phenomena to bare essentials. So to understand what is really important and what is secondary. Okay? Now, black holes, of course, they are objects in gravity. And for sure, in order to ask and answer all these questions about black holes, all these fundamental questions, you would need to go through quantum gravity computation. I don't think we can avoid that. And quantum gravity has an easy part and a very hard part. And the question is, what is secondary? Okay, so can we somehow try to understand black holes by putting aside secondary irrelevant complications and really understand what is the key point? Okay. In other words, what comes really from the complications of quantum gravity and what is universal and may be shared by other systems of nature. Okay, so that's the question. So for this, first let's ask questions that we want to answer. So this lecture, this school is about black hole information. So that's what I will be focused on to understand black hole information. And so let's first try to understand what are the questions that we want to ask, right? Now from the point of view of quantum information, as you know very well, black holes are really fascinating because they have extremely interesting and seemingly unusual properties, okay? So for instance, let me see, so I will start from here and then we'll list questions there. So let's say we know that black holes, they saturate bound on information storage capacity. Okay, so you can ask this question: if I give you a box of certain size, certain radius r, right? You can ask this question: what's the maximal amount of information that you can put in this box? Okay, and the information is bounded by Bekenstein bound. Actually, also people in information theory, they used more or less the same time similar bounds. So this tells us that the maximal is something like the energy that you put in the box times the size of the box divided by h bar. Now, I will keep c, the speed of light 1, okay, in this discussion. So basically, whenever I discuss no relativistic limit, of course, c will be infinity. In relativistic case, c will be 1, okay? But h bar I will keep explicit often, okay? So this is the maximal amount of information. Why? Because information costs energy, right? In quantum mechanics, you have to invest energy. But energy gravitates, right? And therefore, there is a natural limit, because if you put a lot of energy in the system, you will increase the gravitational radius. And eventually the gravitational radius will be equal to the size of the system. And this means that that's it. You have to stop there because your box became a black hole, right? So when this happens when the energy of the energy that I invest is given by a mass of a black hole, and there is a relation between the mass of a black hole and its gravitational radius that we know, right? So this relation is now d is space dimensions, okay, dimensionality of space, and L Planck is the Planck length in that space dimensionality, okay? So as you know, it's a fundamental length of gravity, and the relation between the Planck length and Newton's constant in that dimension is this. Basically, h bar times Newton's constant has a dimensionality of area. Okay, so remember this. It's an interesting fact. And so this is the Planck length. So in terms of Planck length, this is the relation between the mass of a black hole and its radius. And now we can understand immediately that the bound is saturated by the entropy. Okay, Bekenstein-Hawking entropy. Because if I plug it there, R over h bar cancels out. And we get okay, so the entropy scales, this is the famous scaling of entropy as area. Okay, so by the way, you can stop me anytime and ask questions, of course. Okay, so the question is, what can we learn from here? Okay. Of course, this is pretty mysterious, this expression, right? Because first, suppose you want to take this seriously and you want to do some kind of bookkeeping from the point of view of a quantum information person, okay? So you have this entropy. What does this mean? Okay, first of all, it means that black hole state, a quantum mechanical state of a black hole, has a label, right? So label J. Now this label goes, it's a hidden label. Why? Because if I'm a classical observer and I see a solar mass black hole, for me, this is just one object, okay? But it comes with a hidden label, a quantum label. And this label, or a flavor, okay? And this label goes from 1 to exponent of S. So in other words, what we think classically is a single object, quantum mechanically actually is one out of exponentially many flavors, okay? So we need microscopic theory for resolving this flavor. Now, so the question is, now you can ask this question, how can I bookkeep this information if I am a quantum mechanical person, okay? So there is one nice way, which is the following, that this scaling of entropy as area creates an impression that you can mentally divide a surface of a black hole by many pixels, okay? And put a degree of freedom, quantum mechanical degree of freedom, a qubit, let's say, okay, or a qubit, that is living in each pixel, okay? So this quantum mechanical degree of freedom, of course, you can think of it as some kind of quantum oscillator with a which can be some two states. You can parameterize these states by occupation number of quantum oscillator, let's say 0 and 1. Okay, so you can have 1 or 0 each, but they have a label alpha because they're different, so they live in different pixels. They have to be different in order to account for the entropy. So then alpha runs from, not from exponent, but from 1 to 2 to s, right? Because this is the number of, precisely the number of pixels, Planck scale pixels. So each of these pixels they have Planck size, Planck area, okay, this area. Okay, and so this looks like in this way we can account for the way black hole entropy and correspondingly the information storage capacity of a black hole scales. Okay. Now, of course, so this idea that you can have degrees of freedom that live on a horizon, and that's why entropy is scaling like area. This is called often we call it a holographic principle. It was pioneered by Toft and Susskind and others later. This, of course, now we are discussing this all the time. So this is the now this is holography. Now, of course, immediately this raises many questions. These are precisely questions we want to address in these lectures. Okay, and let me start listing questions. I don't know how many questions I will need. Let me start from here. Now, the first question you can ask, are these degrees of freedom real? Or this is just a sort of some kind of a bookkeeping, it's an extremely useful bookkeeping, but they are not really real degrees of freedom. They're just simply a way to parameterize our ignorance about the way entropy emerges in a black hole, right? So therefore, so is holography real? Now, if it is, I will argue that it is real, actually, and not only that it is real, and actually there is a huge class of systems with enhanced memory storage capacity, which actually are holographic, okay? And since it is real, then of course the natural question is, I mean, what's the microscopic origin, right? Of qubits of these degrees of freedom of holographic modes. And there is a separate question why. So first, why they emerge? In other words, how come a system that initially doesn't have any gapless degrees of freedom, when you push it to form a black hole, all of a sudden releases an enormous number of gapless degrees of freedom? So the first question is, what's the mechanism behind the emergence of a gapless degree of freedom in a theory without really having any gapless degrees of freedom to start with in a finite volume? Okay. By the way, gravity has no gapless degrees of freedom in a finite volume. Gravity has graviton, which is a massless particle, but the gapless degree of freedom is only infinite wavelength graviton. The moment you want to focus on a system of finite size, a priori there is no gapless degree of freedom available, even in gravity. Okay. So, and then, of course, why the area law? Why there are number scales like area law? Okay. So what is this shock is a disaster. So what is the scaling? What is the microscopic origin of the area law, right? Okay, so now, what else? What else do we know about black holes? Now, we know about black holes that they evaporate. They, in other words, viewed as quantum mechanical states, they are unstable. They are sort of resonances. If you ask a quantum field theorist, what is a black hole is just an extremely long-lived resonance, okay? So it takes centuries, a lot of time, more than centuries to decay, usually, but it decays extremely slowly, okay? Very good. So it decays, but decays is, as you know very well, extremely strange. Why? Because it decays by evaporating, so it's a Hawking evaporation. right? But Hawking evaporation is not carrying away, it carries away energy without carrying away information. And this is very strange, because you have an object that decays, gives away energy, looks like it literally is disintegrating, but is not giving you the information that it hides. Okay? And this is extremely strange. Now, for a long time, of course, so therefore, the question number 4 would be, why it gives away, or releases, let's say, energy, but no information. Well, of course, no information for a long time. Finally, of course, it has to release information for a very long time. Because in this lecture, I'm not going to assume that quantum gravity violates unitarity and these kind of things, okay? So therefore, this is the question. Now, of course, sometimes you can even ask what's the decay mechanism to start with, viewed microscopically. That's part of it, okay? Now, how does this work? Okay. Now, okay, so these are the facts, okay? So we know these facts about black holes. Yeah, you have a question? Yeah. Oh, everything has entropy. We'll discuss that. So basically, Hawking radiation, so in other words, in the limit, so there is a special limit. This will come. But let me explain. So there is a special limit in which this Hawking radiation has been computed. Okay? So in other words, we know how to compute, was computed by Hawking, and we know how to compute it. And there's a special limit. Now, what is this limit? This limit is when you ignore any quantum back reaction from outgoing radiation to geometry. Okay? So in other words, what you have to do, you have to take an artificial limit in which you take a black hole mass to infinity, Newton's constant to 0, but keep the gravitational radius fixed. Okay? So what happens in this way, in this limit, is that effectively the geometry becomes absolutely rigid. So you cannot do anything with geometry. You cannot back react on geometry. And so in this limit, we can compute it. And in this limit, this so-called semi-classical limit, basically, okay? So now computed in this limit, the Hawking radiation is exactly thermal, okay? So the spectrum of Hawking radiation is exactly thermal. And that's why it cannot carry any information, because it's just a thermal spectrum. It has no other characteristics other than temperature. From that point of view, okay? So now, of course, we understand that for real black holes with finite mass, temperature changes, because since black holes evaporate, the black hole evaporates, it loses the mass, and temperature changes. And actually, if you can evaluate I will not do this now at the moment, but you can evaluate very simply the time derivative of temperature divided by temperature, this parameter, okay? And actually, you can see that it's inverse entropy of a black hole. So, in other words, corrections are not exponentially small to thermality. Now, since temperature changes, obviously, you cannot have, there are no systems in nature for which temperature is time dependent and they are in exact thermal state, because it's obvious that something is happening with the state, okay? The interesting question is what is happening with the state. So anyway, in other words, already from semi-classical reasoning, there are indications that something should happen. So there should be some effects, some corrections that should encode information, obviously. The question is that these corrections, they take too long before you can read out the information if you are an external observer, okay? So for an extremely long time, the decay is essentially going on, but is not releasing the information, okay? Now, we will discuss these things in more details. Okay, so now, these are facts, and there are other interesting questions, okay? And these questions are related with, now this is a conjecture, okay? So now from facts we are moving to a conjecture. And conjecture is about scrambling of information. So it has been conjectured by Hayden and Preskill and Sekino and Saska and others that the information which is maintained by a black hole becomes scrambled very fast. So there is even a conjecture which is called fast scrambling conjecture. Okay, now how fast we will see during the lectures, okay? So if we assume that this is really true, and actually it will, as I will show, this is true indeed, in that framework that we will discuss, then what's the microscopic origin of scrambling, okay? So there is this question, okay? All right, so now what I want to, I want to proceed, as I said, with model building. In other words, the question that I'm interested in is the following. Are these properties, okay, exclusively the properties of quantum gravity or gravitational system, okay? Or they are universal for other systems that could store and process information efficiently. What does it mean efficiently? I will explain in a moment, okay? So in other words, the conclusion, what I will show you is that we will see that actually these properties seems to be a universal property, all of them actually, all the properties, it seems that they are all universal, for a huge class of systems with enhanced memory storage capacity, okay? Now let me define first what I mean under this property of enhanced memory storage capacity. Now the system, so when we store information in a system, we always use some degrees of freedom, right? The first thing that we need to identify about the system, whether this is a black hole or a human brain or whatever, right? What are the relevant degrees of freedom, okay? Now, there is no universal prescription for finding relevant degrees of freedom. Why? Because relevant degrees of freedom, they depend on the energy that you are operating at and convenience, okay? So, for instance, in this room, if I'm interested in understanding physics of this room at distances much larger than intermolecular separation, okay? Sound waves are perfectly nice degrees of freedom, okay? But of course, if I'm interested in distances much shorter, let's say than the QCD length, I cannot use sound waves in this room to describe that, right? So therefore, the convenient degrees of freedom, they change when I move from one system to the other, okay? Now, the general requirement that these degrees of freedom should satisfy, almost always we pose this requirement, is that Hamiltonian should be nearly diagonal in these degrees of freedom. So in other words, you see the picture is the following, right? So you have a system, let's say, I don't know, this table or something, right? And this system is a quantum mechanical system. And there is a huge infinite Hilbert space. Even one oscillator has an infinite Hilbert space, right? But in practice, when you are interested in certain process, you never explore infinite Hilbert space, okay? Always any finite duration process explores some finite part of the Hilbert space, okay? So now, therefore, it's always useful to identify degrees of freedom, the ones in which off-diagonal terms in the Hamiltonian are less important than the diagonal ones on the relevant part of the Hilbert space. Okay? I cannot make this requirement universally. Always there is some part of Hilbert space where I can arrange that. Okay? All right, so then these degrees of freedom typically we can understand as quantum oscillators, okay? With some creation annihilation operators, okay? Now they satisfy usual algebra, creation annihilation algebra. And different ones commute. Okay, so now these degrees of freedom, they have a label, right? So this label, of course, again, is a matter of convenience. It's a question how you want to label your degrees of freedom. So if you're looking at the neural network, your degrees of freedom are neurons, and you just label them, let's say, by position in your network, okay? In quantum fields, we label these degrees of freedom by their transformation properties with respect to the symmetries of your Hamiltonian and symmetries of your vacuum, right? Because that's the most convenient one. So therefore, typically these labels in for quantum fields are momentum. They label momentum, spin, etc. Okay, for a field. So you have this set of these degrees of freedom, right? And you want to store information in those degrees of freedom, okay? Now, you can store information in the states of these degrees of freedom. So there are certain states, right, in which these degrees of freedom could be. And you have a reader that could identify information hidden in those states. Now, the reader depends, because sometimes the reader may resolve certain features of your state and may be blind towards other features, okay? So it depends who reads it, okay? Now, for quantum information, right, if it's a quantum field, the quantum information, we can store information in the states of these oscillators, and we can introduce a basis, a very nice basis, which will be occupation. So each oscillator will have a occupation number operator. And so the information we can store for instance, in the eigenstates of number operators. Okay. So you can introduce a basis in this way, and then you can store information either in occupation numbers or in their superpositions. Okay. So then you can do whatever algorithms you want. Now I will call this space in which the basis is this number of operators, Fock space. Of course, this is a Fock space. I will call this a memory space, okay? So for me, this will be a memory space. And the memories are encoded in this space in form of this sequence of these numbers, and these numbers, they form some patterns. So you can think of them as some sort of pattern vectors. As I said, the rest is the question of algorithms and a reader. You can encode differently information in those numbers. Okay, that's up to you. Okay, so now, each state corresponds to a pattern, and each pattern costs an energy. Okay, so there will be a typical energy cost of a pattern, which will be the expectation value of a Hamiltonian of your Hamiltonian on a given state, okay? Let's say these are basis patterns. We can use them as basis patterns, as basis. And so there will be some energy cost of a pattern, okay? Now, if you give me unlimited energy and forget about gravity, of course, for a moment, as we discussed there, I can store infinite number of distinct patterns, okay? But that's not the way systems work usually, because the energy efficiency is very important. And so the energy efficiency of the memory storage, I will define in the following way. So there is an energy, and there is a certain reasonable gap, okay, of energy. Some reasonable elementary gap. So some unit in which you want to measure microscopic physics of your system. Okay, it's up to you. Could be electron volt, could be whatever. Depends on the problem. So we agree on this elementary gap, and then the question is how many patterns This means how many distinct basis vectors in this way can I fit in this gap? Okay, what's the number? The number of patterns. And so the systems of enhanced memory storage capacity are the ones that can store maximal number of patterns within the smallest energy gap, okay, within the minimally narrow energy gap. Actually, not surprisingly, this capacity is saturated by black holes. That's what they do, okay? All right, so very good. So now we know what we are looking for, right? And now the question that we want to understand is how black hole manages to achieve this efficiency of pattern storage, because the efficiency for black hole pattern storage, if we take this picture, as we said, this is enormous, right? It's the number of patterns that it can store is exponent in the entropy, okay? So for instance, to give you an idea, if you take a black hole of 1 centimeter size, right? The number of patterns for a black hole of 1 centimeter size, let's say 1 centimeter, is 10 into the power 1066. Okay, so this is now you cannot imagine any real normal box that you can manufacture in laboratory, 1 centimeter size, in which you can fit this number of patterns with that energy cost, okay? So already these numbers are really impressive. They tell us black hole is doing something really incredible, right? Okay, any questions so far? Yeah.
You want to find energy efficiency for a general system, it's this n divided by the delta V.
Exactly, that's right. Right.
Are you holding the linear system size fixed? Or?
Yeah, no, I'm just saying you have a certain system, right? I'm always comparing systems of the same size. We have to fix something. Either we have to fix size or something else. So yeah, good. So there is no, again, I'm saying there is no universal recipe. This is just for convenience, that's my definition. Because it fits very nicely the questions that I want to ask about black holes, okay? At the end of the day, these lectures are not about algorithms, okay? These lectures are given by a physicist that is trying to understand energy efficiency of the information storage, okay? So, but yes, of course. So typically, to compare, either we compare energy, fixed size, or we compare fixed size and fixed energy. It depends. We'll see. Okay. In every example, it will be crystal clear what are we looking for. Okay. Anything else? All right. So now, then so how do we proceed? So we proceed in the following way. So I can use the other blackboard, right? Also. Let's see. And now, yeah. Okay, so now, what do I think? Okay, so now we'll proceed in the following way. We'll have two observers, okay? Alice and Bob. And now, what's the difference between them is that Alice is working with gravity, okay? So here is gravity. And Bob is trying to translate the results in a different language, in a language of either quantum field or a neural network. Okay? So now they are given the same task. So so Alice is given a box. So first Alice. We give Alice a box of certain size, certain radius r, and we ask her to maximize the memory storage capacity to store as many patterns as possible within that box. Okay. Now we give Alice, so we can give gravitons and photons or other particles, but it's enough to give gravitons. So Alice is a quantum field theoretic person working with gravity. So for Alice, gravity has degrees of freedom, gravitons, okay? And so using gravitons, somehow she has to store patterns in this box, okay? For this discussion, for this part of the discussion, gravitons or photons, it doesn't really matter. So they're particles, and so she uses particles. Now she has to identify these degrees of freedom in which she can store patterns, okay? And the degrees of freedom are obviously different helicities and momentum modes of a quantum field. Okay, very good. So now, first it's clear that if you want to store in a box a very sophisticated pattern, it should have many features, right? Many features means that you should use short wavelength quanta, okay? Because then you can put more information into short wavelength quanta. Now this is, of course, has immediate understanding in this quantum language. Why? Because the number of quanta with a given wavelength, up to a given certain wavelength L, okay, that you can fit in the box, scales as the volume of the box. Okay, so the number of these degrees of freedom, let me call them M. Okay, it's not a mass number of degrees of freedom. Yeah, in this discussion, I'm short of notations. So M is I don't know. M I don't like. So let me call N tilde. Okay, M number of modes, different modes. Okay, different species. Don't confuse. So important thing during my lectures would be not to confuse three different numbers: the number of different species of modes, okay, with the occupation number of each mode, all right, and with the entropy count, okay, with the mode. So number of patterns. So the number of modes, as you know very well, scales as as the volume in units of L. Okay. Okay, we set some ultraviolet cutoff, for instance, a Planck length, and so that's the number of modes available for Alice to store information. Okay. Now this is a huge number of modes, and naively, if I'm a naive person, I would say, oh, if I have so many distinct modes, the pattern that I can form out of them will be so long, then the entropy will scale like a volume of the system. But we know that entropy doesn't scale like volume in Planck units. Why? Because it's not that the number of modes that matters, but what matters is energy efficiency. In other words, how many of those modes can you actualize at a given time for pattern storage? Okay? Because you can have huge number of modes, but if you cannot actualize them, then they are useless. You cannot store patterns in those modes. Okay? So that's the point. Now, obviously, immediately you can see that if Alice is very naive, if she says, okay, look, let me ignore interaction, gravitational interaction among these modes or whatever, okay? And simply, let me store a pattern. What would be the entropy? Entropy would scale like a volume. But what would be the energy cost of a pattern, right? The energy cost of a pattern would be, right, if I actualize all of these guys, most of the energy comes from the shortest wavelength ones, and energy will go like h bar divided by L Planck times this number. And now notice I can use relation between the radius of a black hole and the radius, and you can see immediately that this number actually is the mass of a black hole of this size times a huge factor. Okay? Of course, we can forget about this. That's the point. The point is that there is no way for you to actualize, despite the fact that these modes are there in the spectrum, there is no way for us to actualize them so naively, because this would cost energy which is way bigger than the mass of a black hole. Now, okay, so now, if we are naive so far, right, and we may think that this is good news, right? Because this looks like this explains why the entropy of a system cannot scale as volume, okay? But actually it doesn't really explain it, because I would get exactly the same problem if instead of this fraction of modes, I would try to actualize a smaller fraction, an area. If I would actualize this number, again, I would be in trouble, because the corresponding energy now with this number, the corresponding energy will be again much bigger than the mass of a black hole with a linear factor like this. So obviously there is something in this counting that we don't understand, okay, how to store patterns in the system. However, Alice knows one thing, okay? She knows about black holes, and she knows about capacity of black holes. And so what she will do is the following. So she will form a black hole first, okay? And after she forms a black hole, she can enjoy the information storage capacity of a black hole. So in other words, for Alice to maximize the information storage capacity of a box, right, is to form a black hole. We knew this from the beginning. But now let's try to understand step by step what may be happening during this process, okay? So we do in the following way. So Alice will create a black hole step by step, and then Bob will try to understand, borrowing some guidelines from Alice, okay, what happens. So now, how can Alice form a black hole in a reliable way? To form a black hole in a reliable way, she has to put particles in a box, right? Now, to count how many we need to put, the best thing is to be on the safe side for particles to be weakly interacting gravitationally, okay? So in other words, the interaction among particles not to affect identity of particles too much, okay? So for this, you can choose the softest modes that you have at your disposal, okay? So there is a box, and so Alice puts a certain number of particles, certain number n of particles of the softness, of the minimal softness, okay? So basically, minimal softness means the particle that you can fit in the box, scaling like, with energy scaling like h bar over r, okay? So she populates this box with very soft particles. And okay, you can estimate very easily how many she has to put in order to form a black hole. That number, not surprisingly, from all these expressions that we wrote there, relation between mass of a black hole and the radius. So when Alice forms n equals to number r over L Planck t minus 1, actually the number equal to the entropy of a black hole, but this is just simply a fact, okay? After that, a black hole becomes, box becomes a black hole, okay? And then she can just use this box to store patterns. Okay, so what are we learning from here? So what I'm learning from here is that something highly non-trivial is happening with these degrees of freedom that store information when the occupation number of the soft mode reaches a certain critical level, okay? So this is the message we are taking from here, okay? Now, what is precisely happening? Alice has no idea, we don't have any idea about this, right? But now what Alice can do, she can give some guidelines to Bob, okay? To ask Bob to do the similar thing with a different system, non-gravitational, and see what happens there. Maybe we learn something from this exercise, okay? So now, okay, so now here's the story with Bob, right? Now Bob says, okay, tell me what to do, and I will try to write down a model, okay, which will be computable, okay, will not be problems with quantum gravity corrections, etc. I can compute things, even exactly, and see whether this phenomena is universal or more general than gravity or whatever, okay? So now, so we can realize this thing in system with degrees of freedom of those type. And there are two interesting realizations. I'm sure there are more, but two interesting ones are, first, the realization in terms of a quantum field, even non-relativistic one, which is even more surprising, and then in form of a neural network, okay? So, therefore, Bob can introduce a quantum field, non-relativistic even, okay? So, let me introduce a quantum field with that lives on a d-dimensional space. Now, the type of the space is not so important. What is important is that the Hamiltonian in the background is rotationally invariant, okay? So the system, the simplest to illustrate the point is a sphere. So therefore, let me take a d-dimensional sphere. And so there is a quantum field that lives on this d-dimensional sphere. Now this sphere has angular coordinates, okay? Let me call them thetas, okay? And has angular harmonics. And there are corresponding the modes of angular harmonics. Now, so there is a spherical, so there is a d-dimensional space, a sphere, and we have a quantum field psi living on this sphere. Now, since we are in non-relativistic theory, this has a crystal clear interpretation. This is simply you have a boson, which can be in different momentum eigenstates, obviously, living on a sphere. And this field simply describes fluctuations of the number density of this boson. Okay, so you have a bunch of bosons on a sphere. Yes?
Why do you restrict to a sphere at the moment?
Because it's easier. That's the only reason. There is no. So once we understand things on a sphere, we'll see immediately that the phenomena is absolutely general, and sphere is not important whether it's a sphere or whatever. What is important is that there is a rotational invariance.
And why?
We'll see. That's the lecture, right? Okay. Right. So, okay, so this is the point. Okay, very good. So now Bob has to write down an Hamiltonian of this degree of freedom, right? So Hamiltonian is the integral. So the sphere has volume element omega and the volume omega, okay? And so the Hamiltonian is obvious. First term is obvious. It's just a kinetic term of particles, okay? So. Now, this is a spherical Laplacian, so let me write it like that. So this is Laplacian, which will be certain energy unit, let me call it E, okay, times a purely angular Laplacian. A purely angular Laplacian, as you know very well, these guys, these y's are eigenfunctions of this purely angular Laplacian with the following structure, right? Okay, so this where omega k is r, k, let me call it kd, the highest weight, kd plus d minus 2. These are simply, as you know, probably most of you know this, just generalization of standard harmonic functions on a sphere. They form an orthonormal set, okay? So these are the eigenvalues. Now, what is important, this partially starts to answer your question. What is very important is that the degeneracy, which I will call figure n, okay, this is n, it's not s, of k. The degeneracy scales as kd in power d minus 1. Okay, so now each k stands for a set of integers, as you know very well, right? They are a set of integers, k1, k2, kd, and these are simply generalizations of the standard LMM spherical numbers. Now, the highest member is, let me denote the k of d, and so the degeneracy is d minus 1, okay? All right, so now, so the first term in the Hamiltonian is clear, okay? The second, what about the other terms? Now, and here is the guideline that Bob has to borrow from Alice. The guideline is that, okay, we want to imitate gravity in a most naive way we can. In other words, what we want to have is interaction between different modes or interaction of the field to be attractive, okay? And energy or momentum dependent, okay? So higher is the energy, to be more attractive. So to be dominated by this, at least in some interval of energies, okay? So now, there is no unique choice of the Hamiltonian. Actually, it turns out every Hamiltonian we can try, you can see that it works. Essentially, it looks like all the Hamiltonians with this property work. Okay, let me choose a simplest form. So let me write it like this, normalize with the, you know what, let me write it somewhere here. Okay, let me enter Alice's territory. So this is Bob again. So and there is an interaction term. There is a scale lambda here, okay, and angular momentum or momentum-dependent interaction. And then, okay, so this is what is important. So then I will put a term which simply makes Hamiltonian bounded from below, okay? So in order to avoid this type of questions, what comes from boundedness of the Hamiltonian. And okay, they're simplest. Okay, let me put it in a convenient form. And plus Hermitian conjugated, which would be okay, so this is our Hamiltonian. This is enough to illustrate the point. So there is this attractive interaction, which is momentum dependent, okay? And then there is a stabilizing term. Okay, so this is what Bob does. Essentially, in an extremely naive way, introduces sort of a gravity-like interaction in the system. And now, let's see if the same thing happens as what happened with Alice when we start to populate the system with the soft modes, okay? Now, let me change the blackboard. Wait a minute. Okay, let me do. So let's do the following thing. So actually we are fortunate here because we can take a limit in which the mode counting becomes exact. This limit is similar to large N limit of Toft in QCD, large N QCD. But there is a difference in the sense that we are not, so in case of Toft, we are changing the theory. So because we are taking large N means that we are taking the limit of, we are taking limit of different theory. But here we will just take a limit in which we explore a particular state in a given theory, okay? So that's the only difference. So what is this large N? This is, let me take soft mode. So Bob is trying to populate the sphere by a soft mode. The softest mode is the zero mode here. We are fortunate, okay, on the sphere. And so we populate the zero mode, occupation number of zero mode, with some large number n. Okay. Now let's make first mode counting exact. So we make mode counting exact by taking double scaling limit. Okay. So double scaling limit means I take n to infinity. Simultaneously, I'll take coupling to 0, lambda to infinity also. But I fix a certain combination. So I fix the combination E over lambda n in power, actually in the following power, 3d minus 1. This is fixed. Now, where is this power coming from? Okay, don't get scared with this power. This is simply a requirement that I'm taking a particular limit in which the interaction terms, okay, the ones that do not involve powers of n, they vanish. It's like a sort of very similar to the planar limit of 't Hooft in large NQCD. Okay. Now, in this limit, the Hamiltonian simplifies enormously. Okay. Why? Because you can see immediately. You will fish out. So lambda goes to 0. So 1 over lambda goes to 0. Okay. So it should be only terms in which 1 over lambda is compensated by n, high occupation of a 0 mode, will survive. Okay. So from here will survive when I substitute these two by 0 modes, and this will give me factor n. Why? Because yeah, I should have said that. Now remember, there is this notion of so-called Bogoliubov approximation. So in other words, we know that when the occupation number of a mode becomes large, we can, up to 1 over n corrections, we can replace the mode with high occupation number with a C with an operator with a C number. Okay, so in this limit, we can simply replace A0 and operators. We can simply replace it by n. Okay, times some irrelevant phase. So therefore, okay, now you see what happens. Sorry. The term that will survive will be when I fish out a 0 mode from here, which will give me factor of square root of n. I cannot fish out 0 mode from here because this is acted upon with the Laplacian. Okay, and from here. So from here and here I cannot fish out a 0 mode. So therefore there will be 0 mode from here. So these two will give me factor of n squared. So therefore these two will give me factor of n. No 0 modes here. And the same story here. So the 0 modes will be A0 square will give me factor of n. A0 square will give me factor of n. And so these two will give me factor of n squared. Okay? And so we can write the Hamiltonian in this limit in an extremely simple form. So let's do it. Okay. Well, should I use that one or? All right. Let me use this one. Let me see if I can manage this. Oh, this is what. Okay, so now, so Hamiltonian in this limit, in this double scaling limit, takes an extremely simple form. So the sum over all decay levels with epsilon k mass gaps, the energy gaps, sorry. Plus interaction terms which are suppressed 1 over n. And the form of epsilon k is most important. So the form of epsilon k is e over omega k 1 minus okay, so what happens? So this is the form, okay? So in other words, for given n, in other words, there are certain levels, k, that become gapless, okay? So all of a sudden, a gapless level emerges, okay? So the level that is gapless is the one that satisfies, so remember, this scale says k, k minus k d plus d minus 2, okay? So therefore, there is a gaplessness condition, okay, which is simply e over lambda k okay, so the levels that satisfy this, they are gapless. Now, what's the implication of this fact? Okay, of course, very important. Why? Because you can see immediately that because of the level degeneracy, the number of modes that emerges, the gapless modes. Now, this is number of modes, the gapless ones. This number goes as R as area, with Lk being omega k of the gapless mode, of the gapless level, okay? So let me call this gapless level k star, all right? So now let's see what happened, right? Yeah.
Maybe I should have asked this earlier, but are you saying you want the states, this large number of states to be truly degenerate?
Well, they are not truly, they are only degenerate in this strictly n going to infinity limit. But for finite n, they are not strictly degenerate. I come back to that point.
Because the naive spacing you would expect is maybe this number of modes in a range of energy that's of order 1 over r.
Exactly, that's precisely the point. So in other words, or to be more, let's make it more precise. So in other words, so these modes, so this is now entropy, which is literal like area. So now, so there are a number of patterns that these modes can store, as I will discuss in a second. So the number of patterns, which is essentially exponent of s, okay, so 2 in power s, or actually exponent in s. I'll discuss in a second. So all these patterns, so they fit within delta E, which is E, okay? So they fit within E, and E is, right, E is h bar over r. Analog of h bar over r, yeah, absolutely. That's correct, thanks. Now, so let's try to understand what happened, right? Because we started with a system which naively has nothing to do with gravity, right? Okay, so there is just simply a bunch of bosons on a sphere, okay? The only little small thing that sort of looks gravity-like is that these bosons have negative interactions, negative energy interactions among themselves, which is controlled by the momentum, by their angular momentum. And then all of a sudden we see that family of states with emergent gapless modes, okay, with the area scaling emerges, Okay, so we have not just one state, but family of states. So for each large n, there are certain relations between certain large n and center k, and those families are give us gapless modes. Now let's plot this. Let's plot this spectrum, okay? So the spectrum is very nice. And has the following form. So it has a minimum somewhere, right? And then goes up. So this is, let's say, for, so this is, I'm plotting spectrum as the function of omega k. Let's say this is for one particular omega k star. Now, n for one particular n that satisfies this relation, right? So this is for particular n, let's say n. Then I can change n, and correspondingly I can change omega. And there is another family somewhere here, omega of k star prime. Let's say I change k star by just one unit. And then the spectrum is like this. It follows for a while, gives higher maximum, and then goes down, and again up. So this is n minus delta n, let's say. Okay. Now this is the spectrum, epsilon k. And now, also it's extremely instructive to plot the spectrum of a would-be free particle. Okay, so the spectrum of would-be free particle would be simply a straight line. So a free particle of the same momentum, as you can see, would have energy gap which is enormous compared to the one that is emerged because of this phenomena. Okay. Now, as we will see, this will be the key why this system maintains information exactly the way black hole does. It simply has no possibility to release it because of this phenomena. Okay. Now, and we'll see that. So for a moment, we are here. So now, so what do we have? We have family of holographic states. Literally, these are holographic states. Why? Because they deliver gapless modes with the number scaling as area. And of course, they have enhanced capacity of information storage. We can populate this, each of these state with patterns. We can form pattern vectors starting from n k, n1 n of number of k star species. Okay. So these pattern vectors, and there is an important characteristics that we need to give, which is the total usage of the memory space. Okay, so let me define a total usage, let me call it n, as the sum of all the occupation numbers. Now, okay, so now we should ask questions how we want to store patterns in which type of states. Okay, in other words, how much you want to allow the occupation numbers to be. So you want to consider 0, 1, or you want to consider 0, blah, blah. Okay. Actually, it turns out that even if you consider, so to really count microstates, okay, so these are now states that form microstates around the macrostates, right? The full state, essentially, the full state is certain n of 0 mod, a tensor product with this, right? So the macro characteristics of the state is the occupation number of the soft mode. So the soft mode gives you macroscopic state. And then around these macroscopic states, there are microstates, okay, which are obtained by small excursions in these different modes. Okay. Now these excursions, you should limit yourself in order for these states to belong to the same ensemble of microstates. We have to limit these numbers by order 1. We cannot take numbers to be much larger than 1. If we take numbers much larger than 1, even if those states happen to be degenerate, you can make that those states are also degenerate, they do not correspond to the same microstate, okay? Because the new macroscopic characteristics emerges which distinguishes them, okay? So microstates, they should differ microscopically, okay? So they cannot differ macroscopically. So therefore, always there is a sensible limit to what you have to restrict yourself if you want to really count microstates, okay? Now, of course, if you want to use this as a device for information storage and you don't care about counting black hole entropy or whatever, then of course you can use any state you like. That's up to you. That's not the point. But the point is that the microstates are really the ones that are obtained as a result of small excursions in occupation numbers. Okay? So this is important to remember. Okay, so now, by the way, how much time do I have?
Until 6:05.
Okay. 5.66, okay. All right. Any questions so far? Yeah.
Do you only consider pure states in the whole space or also mixtures?
Well, you can form mixtures. Here I'm considering only pure states.
But pure states have zero non entropy.
No, each state, of course, has zero entropy. It's just one state. So there is one state. Of course, the state itself has zero entropy because it's only one. No. The entropy is the log from the number of microstates. And the microstates are obtained by populating these numbers by zeros and ones. That's what I limit myself, okay? I'm limiting myself by zeros and ones. I could make it bigger, as I just discussed, okay? So all possible states with these nj's being zeros and ones, they form a microstate ensemble around the same macrostate. And the entropy, the microstate entropy, is precisely the logarithm of this degeneracy, okay? With one state, of course, how can you get entropy? My microstate entropy, okay? This of course, this is important to understand, otherwise the whole story is confusing. Okay, so in other words, what we have uncovered is that this system, in a certain sense, behaves like a black hole in the sense that there is a macroscopic label, occupation number, okay, and there is this occupation number of a soft mode, capital N. This is a macro characteristics of a system. This is macro, and on top of them, there are microstates around this macrostate. And these microstates give you a hidden label. And this label is simply a set, somehow numbered set of zeros and ones that you can obtain out of these numbers. Okay? So now, if I limit myself with zeros and ones, then the memory state that will be formed by these guys will have dimensionality 2 in power nk star. So that's the memory state. That's the memory space. Now, okay, so now we should ask several questions. So let's try to understand first. Let's try to understand what happened. How this gaplessness happened, okay? And here's how it happened. So Bob was populating the sphere by soft modes, okay? Now, if I want to excite a mode with high momentum or high angular momentum in a vacuum, this is the energy I have to pay, okay? So this amount of energy for a free particle, okay? So I just have to invest energy, which is enormous. In other words, there is an excitation threshold for an oscillator of a given momentum mode, and you need the energy in order to excite this mode. So to populate this mode with 0 instead of 0, to populate it with 1, and to store a pattern in this mode, you need to invest energy. Now, when I populate the system with soft mode, A0, what happens? Because there is an attractive interaction between different modes, every time I add a soft mode into a system, this soft mode, because interaction energy is negative, lowers the threshold of the excitation of a hard mode. So in other words, what happens is that the soft mode, okay, in this particular case, a zero momentum mode, makes the excitation threshold of a hard mode smaller. Right? In other words, I can understand this n here, right? I can understand this n here as simply 1 minus interacting with the A case, right? So you see what happens immediately. This is what happens. This is my Hamiltonian. So if the soft mode is not populated, right? I don't know if everybody can see here. If the soft mode is not populated, then the threshold, the price to pay in energy is enormous. But every time you populate a soft mode, the energy price goes down because of negative energy interaction. So every time I add a particle, to excite a high momentum mode becomes easier and easier. And there is a critical point at some point where it becomes infinitely easy to excite, where once the occupation number becomes n, which makes this 0, this 1, then essentially the mode becomes gapless. That's the point. So this is what happened. So what happened is that in the vacuum, the hard modes were extremely expensive in energy. But once the hard modes are together with soft modes make them less expensive in energy because of attractive gravitational interaction. Okay? And the critical point is the point where the hard modes, a certain family of hard modes, becomes gapless. Now, when okay, so now we can ask several questions. Now the question is, okay, very good. Let me now enjoy this holographic state, okay, and store the entropy, or store information in these emergent gapless modes, okay? The first question to ask is, where is this area law originating from, right? Is it generic? Why it happened? We see immediately why it happened. It happened because the Hamiltonian was rotational invariant. And since Hamiltonian is rotational invariant, and we are, so in other words, here's the picture, right? The picture is, so we have a system, and this system costs a lot of energy. And now I start populating the system with soft modes. So the system starts to cost less and less energy, okay? Goes down, and at some point it touches 0. Now it touches 0 for a particular momentum mode, okay? So you have to make system like totally crazy for it to touch to touch 0 for continuum of momenta, let's say, or for many momenta together, right? So typically what happens is that you touch 0 at some particular momentum, or let's say 2 momenta, but you don't touch 0 at a continuum number of momenta. Now, since you touch 0 for a discrete set of momenta, right? Because of rotational invariance, the degeneracy is always spherical. It's always, where is it? There. Degeneracy is always area law. So in other words, area law is a consequence of two things. Criticality, that makes the mode gapless, and the fact that the Hamiltonian was rotational invariant, and the background is rotational invariant, at least approximately. And therefore, the degeneracy of level that touched 0 scales as the area of one dimension less. So it scales like d minus 1. It scales like an area of a sphere of d minus 1. Okay? And this looks totally generic as long as your system has these properties. Okay? So therefore, we can say, okay, so maybe we are on a right track and try to understand more properties. Okay? Now, of course, we can ask several questions at this point, right? We can ask question, okay, is this a coincidence? Right? So is this simply a coincidence and the way black holes deliver entropy has nothing to do with this? I don't know. I mean, if you want my opinion, I think no, it's not a coincidence. This type of coincidences usually do not happen. But even if it's a coincidence, it would be extremely interesting, because this would mean that you have other systems of nature that do not share anything with black holes, yet they have all these properties of area low entropy, and as we will see, the list of these other properties. Okay. So since I have only 5 minutes, let me outline the next step. So what we will see, how we'll see this story. Okay, and then finish with this. Now, first, evaporation. Okay, so this means that at the level of this system, we understood first two questions at the level of this particular system. Okay. What about this? Okay, number 4. In other words, now if I allow this system to decay, what will happen? Okay. I'm not going to discuss in today's lecture. I will just outline. Now, in order to allow a system to decay, you have to couple this system to another system. Okay, right? So you need some kind of sector. So I had sector psi. You need some sector chi, so that the quanta of psi could go into the quanta of chi. Okay. So if you want to think in terms of a prototype, think of this chi quanta as the free gravitons or free photons of the Hawking radiation. So now you are coupling a system which is critical and exhibits this gap to a system that is free, right? And you allow transition, no problem. So you can allow transition in which the zero mode of psi goes into a zero mode of chi. Okay, so no problem. You can have transitions into one B or two Bs or whatever. Okay. Now we have this transition, and you can ask this question, right? Naively, it looks like the moment I allow system to decay, to release energy into some external quanta, it will also release information. Okay. Let's see if this is true. Actually, as we will see, this is not true. Why? Because of the following reason. When system decays, it releases soft quanta into soft quanta. But the information stored was not in soft quanta. Information stored was in extremely hard quanta with extremely high momentum, but which became gapless because of criticality. Now, if you want to release information, what you have to do, you have to rewrite the pattern stored in this quanta, this pattern, into the analogous quanta of outgoing chi's. This is impossible because analogous quanta with analogous momenta of chi's, they cost so much energy that it's simply impossible to rewrite the pattern. So what happens is the system decays, but is forced to maintain information. This is one effect, as we will see. We will see this all, everything in details. This is one effect. Another effect is that actually the usage of the memory space itself makes the system to slow down, the decay to slow down. That's another effect. Okay. So what happens instead? So in other words, this is the picture, right? So we are here, and we have pattern stored here. Now system decays. So it releases the background, the constituent soft quanta, it takes away. So what happens? Since n changes, the level that was gapless is no longer gapless because we moved here, right? We changed n from here to here, so we moved here. Now a different level is gapless, and this level acquired the gap. Okay, so this is the process. The process is this level comes down, and this level goes up, and they meet here, right? So they meet somewhere. So what happens is the system has pattern internally, but it has to rewrite the pattern from this level to this level. Okay? So in other words, to decay, it has to maintain the pattern internally because you cannot release it. That's simply impossible. But it's forced to rewrite the pattern internally. And this rewriting, as we will see, makes pattern completely unrecognizable. It scrambles it. Of course, the process is unitary. Everything is unitary. We are in unitary theory. But the pattern becomes extremely scrambled. Precisely this fact that it is forced to maintain it internally is what makes it scramble. So this process of rewriting from here to here. So basically, to summarize, as we will see, all these properties are exhibited by the system. Now, another thing is that this system, so here we understood it as a quantum field. We can understand it also as a neural network, which is also cool because this means that neural networks in general, we don't think about them as quantum fields, but we think about them as some kind of completely mathematical construction or whatever, okay? But actually, we can rewrite this system as a neural network. And we see that this neural network, once we demand from this neural network that it has enhanced capacity of information, of memory storage, of information storage, behaves exactly the same way as quantum field or as a black hole. So somehow what we will see, what will emerge, is that it seems that what controls all these phenomena is the memory storage capacity. Somehow, the moment you force a system to be critical and to enhance the memory storage capacity, all these phenomena follow. So it seems to be the universal properties. These are universal properties for every system that has, or maybe if not every, a huge class of systems which have exponentially enhanced memory storage capacity. And this is sort of fascinating because this seems that therefore now we can sort of think about many interesting applications because this looks like that, and then it could be that, for instance, systems that are also good in memory, they sort of use the same universal phenomena as black holes to store information and to process it. Okay? Okay, so let me finish here, and if there are any questions, I'll take it. Yeah?
Can you say something about the temperature dependence? So I could
Yeah, temperature was another thing I didn't mention. Right?
differences, so if you
Yeah.
want to store more information, then temperature has to be lower, because otherwise it would have some fluctuations which would erase your information.
Okay, so this is an excellent point, excellent question. By some mysterious reason, I forgot to mention temperature because I was so carried away with this information that, so here we have to be very precise when we say what do we mean under the temperature of this system. So in other words, at this level of discussion, what I have is that the moment you give me these external modes, right? And coupling between them. After that, I can compute, or we can compute, in the unitary process, how the state decays. So we can compute spectrum of chi particles. Now, this spectrum, of course, is not exactly thermal. There is no need to be exactly thermal because it depends how you couple chi to psi. Okay, but there is one universal property that is always thermal-like. In which sense? Thermal-like in the following sense. After all, what is thermal spectrum? Thermal spectrum is a spectrum which is peaked, sharply peaked for some given momenta or for some given energies, and is exponentially suppressed for high, and phase space suppressed for low. That feature, of course, will be here. And that this feature is, again, universal, because the moment you say that your system is made out of soft quanta, and these soft quanta, they leak out into other soft quanta, soft quanta cannot produce hard quanta. That's always exponentially a price to pay. So from that point of view, the sort of thermality, approximate thermality of the spectrum is also a feature of this type of systems. Now, I don't talk about thermality from that point of view because, for instance, for neural networks, this would be like chi would be some one layer and psi would be another layer. Okay. Now, for me, this process is simply you are de-exciting one layer and you are exciting some other layer. Okay. Okay. From that point of view, you can think of it as a thermal, sort of approximately thermal spectrum of this layer that you are exciting. That should be absolutely excellent language, but yes, yeah. More, I would say the spectrum is soft. So is thermal in the sense that spectrum is soft. It's picked around the constituents of the moment. By the way, this thing, okay, we are studying now with some people here numerically, etc., etc. So it's not a finished. I mean, there are plenty of models to play around with and see what happens. Okay. Yeah.
Black hole that's evaporating, then are you saying that the information does come out in the...
At the very end.
At the very end. So
yeah, in this model, that's what happens.
Something that ends up being something like a Planck-sized remnant.
Not really Planck size. No, you see, okay. So yeah, let me explain. So that's a very good point. In other words, you see what happens is that here I'm working in large N. Of course, this is large N analysis. So in large N, we can see, even analytically, it's easy to see what happens, is that, so you have a pattern, then N decreases, and N cannot decrease without rewriting the pattern. So it rewrites pattern internally because it cannot rewrite it externally. And during this process, this pattern is extremely scrambled. Now the question is, okay, until what time this system can continue to maintain this pattern internally? And we see the answer here, because until time that, what happens is that the spectrum, right? Once you decrease N, becomes closer and closer to a free spectrum. You see what happens, right? So it's crystal clear from here. Right? What happens is that then it's closer and closer to a free spectrum. And so at some point, would be energetically not favorable anymore to keep pattern internally. And that's when it will be released. Now, this is an excellent question precisely to study when and what is the scaling of N. Now, if you ask my opinion, I mean, it would be a total miracle if the scaling in this model also reproduces scaling in a black hole of that time scale. That I would not expect that much. I mean, there are limits probably to the applicability of these toy systems. But it's a very extremely interesting question to understand what is the time scale after which the system is forced to release the pattern. Yeah, for sure it's macroscopic. In other words, for sure you can see already analytically in this model that the time scale on which the pattern will be maintained internally goes like a page's time. The scales like N or whatever. Okay, so the page's time in quote unquote. But okay, to be that's for sure. It's macroscopic. But in principle, it could even happen that this time scale is way larger than the time scale in a black hole. That could be. So because this system, of course, is not a black hole. I mean, it's just a sort of very extremely crude sort of imitation of gravity. So for me, what is more surprising is precisely that this system is so remote, and yet it captures so much of these universal properties. So somehow, for me, this is the message that somehow this information, these laws of information are sort of universal, and so yeah.
The second question is, I realize this is only one model.
Of course.
If the black hole really were constructed somehow like this, there's a question of how you would get something that looks like it has approximately the correct semi-classical geometry.
Yeah. So this will be actually, yeah, absolutely. So this will be subject of my third lecture. Sorry, third. So I have two more, right? Yeah, third, because next, probably I will start that next lecture, but will not finish. Yeah. So after these toy models, I'm gonna go to gravity, real gravity, and see how much we can learn. I mean, with using these ideas, how much we can learn about real gravity. So I will present those in probably second half of second and third lecture. By the way, there are also very interesting indications that black hole indeed can be described. I'm not saying it is necessarily, but it can be described as a multi-soft graviton state. For instance, scattering amplitudes that we computed with Dieter and Stiefberger and Cesar and these people, for instance, that's very interesting indication. What we computed is we computed 2 to n graviton scattering amplitudes, okay? By some mysterious reason, this has never been computed. I don't know why. And so for us was very surprising that we see the entropy suppression in this process. Okay, so which was sort of a real surprise because naively this is a computation in terms of Feynman diagrams, and it's true that we resummed the infinite series of Feynman diagrams, but still it's extremely surprising to read such a non-perturbative information from the scattering process. And actually, yeah, that's what happens. There was also a paper by Veneziano and Dazzi and Bianchi doing this similar computation. Yeah. Right, yeah.
Can you comment on quantum chaos in your model?
With this scrambling, you can think of it. So, okay. So this really brings me to the story of my next lecture. So in other words, this chaos, the question with the chaos is related with this question of scrambling. Okay. Now, as I said, there is this so-called fast scrambling conjecture. Okay, of black holes, and I mean, for some time, my collaborators and I, and many other people also, of course, are thinking about this, but we were trying to understand this from the microscopic point of view. And we saw that there is one clear regime of scrambling when you have, in this type of models, by the way, and that regime of scrambling happens when you have Lyapunov exponent, classically, so there is some classical instability in the system. And so the classical instability and chaoticity of the system is what gives very efficient scrambling in the quantum picture, okay? Now, that's one type of scrambling. Now, the thing here that is interesting is that here there is no obviously visible Lyapunov exponent. You see, because this is the entire process is quantum. I mean, it's just simply quantum mechanical, you go from here to here. So therefore, if this is true, I mean, if this, so the question is, what's the origin of scrambling for a black hole? Could be 2 different mechanisms that work. Which one is faster? That's, again an interesting question. So these things are interrelated, and we'll discuss some of them in great details about this scrambling and Lyapunov exponents and this kind of stuff, yeah. Dieter has a question.
When the system becomes critical, meaning gapless, do you know whether the system also becomes conformal?
Yeah, by the way, yeah, thanks, because I forgot to mention. Yeah, in certain sense, it's as conformal as non-relativistic theory could be, because you get, literally, gapless modes with the interactions that are 1/n suppressed. So, yeah, it's true that it's sort of a
conformal algebra whose central charge maybe
but it's very cheap. It's almost trivial that you have it. So you have approximate conformality because you have a set of gapless modes with all the interactions suppressed by 1/n. So it's like in large n limit, this becomes a theory of free gapless modes. It's as conformal as anything could be, right? I mean, just they don't have energy, they don't interact. So it's yeah. But yeah, thanks for pointing this out. Yeah, so this of course gives another set of questions. For instance, whether emergence of CFT could be understood along the same line. Somehow, maybe we can think of ADS, for instance, as some kind of a multi-soft graviton state, and then think about the CFT as some kind of critical, these gapless modes that emerge on that state, and this kind of stuff. So absolutely, yeah. Yeah.
A large number of modes can be, there is a species problem for the energy boundaries. Can this be the number of species?
Yeah. So the problem. Yeah. What he means is the following thing. Let me clarify this because. Sorry. Wait a minute. Actually, I should not erase. he asks about so-called species problem or question. By the way, I need to say that there is no problem with species in the sense that, so the point is that if I have a quantum field theory, now we're talking about gravity plus a quantum field theory, okay, with certain number of species, let's say n species, okay? So then what happens, so this counts not the number of gapless modes, this simply counts number of independent quantum fields, okay? Let's say in d dimensions. So then, let's say in 4D, let's take 3 plus 1 dimension for simplicity, right? So then, in this theory, you can show that there is a fully non-perturbative argument based entirely on black hole physics. I have shown that. That tells you that in this theory, if you have many species, the gravitational cutoff, the strong gravity scale, cannot be M-Planck. That's impossible. Instead, it has to be a new scale, let me call it M star, which is M-Planck divided by number of species. Okay? Now, this, okay, there are several arguments in this favor, but the black hole is most model independent and most transparent. And the point is very simple, because this semi-classicality parameter that I can define for a black hole, right? I can ask this question, I mean, when is this semi-classicality parameter becomes less than 1, all right? And so if semi-classicality parameter becomes larger than 1, then black hole is for sure no longer semi-classical, okay? And so this parameter is proportional to the number of species, okay? That's the point. So therefore, the number of species enhances this parameter, okay? Why? Because if black hole evaporates, if you have more species, a semi-classical black hole should evaporate into equally, democratically, into all the species that are lighter than the temperature of a black hole, okay? So in other words, the Stefan Boltzmann law of a black hole, let's say, right? M dot. This should be T squared, but proportional to the number of species. So therefore, what happens is that the number of species makes black hole emission more efficient. And so black hole goes out of semi-classicality regime earlier. So that's why quantum gravity cutoff comes down inevitably if you have many species which can interact with gravity. So I would not call it a problem. I mean, that's what happens. And by the way, you can check, for instance, in string theory, you can check that theory self-consistently takes care of it. For instance, you can check that in string theory, the rules of compactification and the way you can obtain species always tell you that you cannot make this scale with effective number of species less than string scale. So you can see that always it is really controlled by quantum gravity. So always the theory takes care of itself. So there is no species problem, but there is species bound, which tells you that if you have many species, then the quantum gravity scale inevitably comes down. So this is absolutely true. No, I mean, there is no, if you add more species, you will have more species, and the same story will repeat itself, literally. So the number of species is not affecting, for instance, black hole entropy for large black holes and things like that. So the number of species affects behavior of the black holes, which are small, with the size comparable to quantum gravity scale. So yeah, those will be affected, absolutely. Yeah. Okay.
Remind you that we leave from here at 10 to 7, from the lobby up there, and now it's